So today, okay, I don't see Mark, but he's the other person who's a part of this talk, so we'll say hi to him when he's here. I'm Jane. I work on PyTorch as a part of Meta. I work on things like optimizers and memory efficiency. So today we're gonna kind of share a bunch of techniques that helps you slay OOMs. And if you don't know what an OOM is, good for you, but it stands for out of memory error. Yeah, and if you're like, oh no, I've never run into one of those, again, good for you. But even if you didn't, all these memory techniques will be very helpful in helping you increase your batch size, which improves throughput, hopefully. All right, let's get started. I'm kind of short, so there we go. Cool. What is the syllabus for today? We're going to start with what consists of memory, what does that look like, and then the potato-y portion, which is the cool portion. We're going to give you a few techniques for how to target parameters, optimizer state, and activations and making them smaller. And the conclusion is, if you are able to apply these techniques and compose them correctly, you should get a brick. And if you're like, wait, what's the brick? Find out soon. Pay attention. All right, so here's a quick whirlwind tour of what a model kind of looks like. If you've ever trained one, you define your model. And with your model, whether it be Llama or Mistral, or if you're cool and you don't do LLMs, that's great. Whatever model you want, this is a general way of thinking about it. It comes with parameters. And with that, with models, and if you want to improve your parameters, you're going to need to optimize them with an optimizer. And the most famous one, the one I like the most at least, is AtomW. Note that at this part, the parameters are the only things initialized. Well, not, and the optimizer state gets lazily initialized later. Okay, the model also gets lazily initialized, but don't worry about that. And when you call your model, like you do model parentheses inputs, that's what we consider the forward part of your model. And as you do that, you will start getting activations, and you'll start saving some tensors. If you were a part of Jeffrey or Horace's talk about activation checkpointing earlier, this is exactly what they're talking about. You're going to need to save some tensors for the backward, and that's where this triangle comes from. And lastly, or after you do your forward, you got to do your backward, and that's when you start building up gradients, which is this green little box here. And when you have that, you can then finally apply your optimizer state to your param update. And so that's how we get this little figure to the right, where you can see that parameters, gradients, and optimizer state are actually very tied to each other. Usually, the parameters and gradients are the same size, and optimizer state, if you're doing AtomW, will be double the size, because it takes 2 state per tensor. And activations, that depends on your batch size. The bigger the batch size, the more memory it will take. The smaller it will take. Great. And if you've ever run a model, it might be really helpful for you to try a memory profile to kind of get a sense of what memory does your model use. If I told you that this is a profile of 2 steps, you can kind of see the patterns I was talking about earlier. You have latent parameters that are just there forever. And then as you do your forward, you're saving tensors for your backward. And as you start your backward, you don't need them anymore, so you can start getting rid of them. But in the meantime, you're starting to record gradients. After your backward, you do your optimizer step, and remember, it's lazily initialized. So boom, you get 2x your params starting here. And note that in step 2, they don't go away. They're there forever, or until the end of your run. Forever means the end of your run. And yeah, step 2 is kind of a repetition of step 1, but built on top of everything you've initialized. If you're like, oh no, I didn't pay attention the last minute, well, it's okay. Our Torch Profiler tool also gives you this breakdown for you. Just so you see here, the red triangle is activations, the blue thing is gradients, and we have your optimizer state and your parameters. And that's how we're going to talk about memory in a very simplified way, and it's going to get us pretty far. So that's how we came up with the little diagram on the right, and you're going to see that little guy a lot. Okay, cool. So of course, we're here to talk about OOMs. And OOMs happen when you just use too much memory, when your memory usage peaks beyond what your GPU has to offer. Yeah, and something really important to notice is in my drawing, I had it where activations is the peak. But really, depending on your device, depending on the model you're running, it can get anywhere, which is why it's important to measure your own memory for yourself. For example, maybe you're on a really small device, or maybe your parameters are just too large. So when you're running your first step and you try to initialize optimizer state, you kind of hit that OOM at the start here. Or maybe you have an even smaller device and you don't even get to the optimizer state, but you start peaking and you OOM at the activations during the forward or backward. And maybe you got past the first step, and in step 2, you hit an OOM because, again, the activations are saving a lot of tensors for your backward. And so in this talk, we're going to talk about how to tackle each of these. Because in the end, and here's where the brick comes in, you don't really want big peaks anywhere. You want to kind of maximize memory usage throughout your whole training loop. So we're going to give you some hammers and show you how to hammer down on these peaks. So yeah, how do we get there? We're going to hammer every peak. So we're going to start with params and then get to optimizer state and activations. Just so you know, this is not meant to be like everything in the world. There's like other techniques out there, but today we're going to focus on quite a lot of these here. So yeah, we're going to start with the parameters. Why should we do that? Well, here's a nice little thing everyone should know. The smaller your trainable parameters, the smaller your gradients, and also the smaller your optimizer states, because they're all very related. So no matter what technique you do to kind of slim down on parameters, if you make them smaller, whether with LoRa or quantization or you're using FSDP, you will naturally get smaller grads and smaller optimizer state. So it's a pretty big hammer you have there when you target the parameters. So yeah, let's look at what LoRa would look like when you do that. The essence of LoRa is to take a linear layer like x equals weight matmul with x to become x equals weight matmul of x plus b matmul a matmul x. And you might be like, why does this matter? Well, in the first stage, you need to train on every W. And W is a big, big parameter. Yeah, and if you are doing that, that means you need big gradients, you need big optimizer states. But in LoRa, you freeze W, so you no longer need to train it. It's still there. Note that it's right there, it's frozen. But your gradients and your optimizer state will only follow what's trainable, which is much smaller. So you can tell that already the memory has been saved a lot, just by training a lot fewer things. Yeah, and we call BNA adapters, just for terminology. We can keep going here. Because your parameters are frozen and you don't really need them to do anything, you're not like updating them across time, you could do QLoRa. You could quantize the big frozen parameters into 1/4 its size. So thanks to Driss, who wrote NF4, we go from BF16 for that big chunk to 1/4 its size by taking every like value in that tensor and scaling it down to a 4-bit value. And if you want to have the details, click on that link. That's the implementation in Torch AO. There's also the paper if you're curious how this is working. But this is how you should think about the memory. But what if it's not enough? What if you do QLoRa and it's still too tall, your memory, and you still OOM? Well, what if we tell you you have 2 GPUs? So in the benchmarks I ran, I actually ran these on 4090s. So if you don't work for like a big company with a lot of GPUs, you might be in this boat where you have 2 4090s. And you could actually do a lot with 2 4090s. So the first thing we should do is, the easiest, most straightforward thing is, okay, that activation triangle really big. Can we just split that in 2? And the answer is yes. Congratulations, this is DDP or data parallel, where you take your data and you're like, give half to each, keep everything else the same on the devices, and we're gonna need to do a little extra logic to sync the grads, but it's no biggie. This is probably the easiest thing you can do. And if it works, great, stop here, go on with your life. But let's say it does not. What if it's not enough? You still OOM. Well, note that we're duplicating a lot of things across both devices. So keep going. You can also shard the parameters. Take your params and cut them in half. And remember our thing from earlier where if you have the params, you have the grads and the optimizer state. So note that it becomes significantly shorter. GG's, this is actually FSDP. And if you've heard FSDP today and you're like, whoa, I still don't understand how it works, we're going to kind of talk about that more. But note that it stands for fully sharded data parallel. So it already has data parallel, and it keeps going, and it shards the parameters into two. This is not entirely accurate. What it really looks like is you have this diagram where there's like a small sliver for each of the machines, because how this works is fully sharded means we're sharding the parameters, and we're sharding the model into a bunch of layers. And at every layer, you're going to pull in some memory from both GPUs. Like GPU 1 will be like, yo, you have the other half of my memory for layer 1. I need that. And the other GPU will be like, yes, you too. So they'll do a little exchange. We call that an all gather. And for that one layer, you're going to need that memory to run the step. And just note that this is not the full thing, because it will be freed once that layer is over. And this is where, because I think it's cool to understand FSDP, we're going to kind of go into this a little more. So it's a small but relevant detour. What is a layer? Like, what does that even mean in FSDP? Well, note that in your world, a model is just a bunch of modules after each other. Yeah. For example, if you're running a llama model, you start with an embedding, and you probably have a bunch of linears. In this example, we can kind of think of the linears as having LoRa applied to them or QLoRa applied to them. But if you're like, I don't want to remember the names, don't. That doesn't matter. FSDP doesn't care about the names either. What it does worry about is the parameters with that like kind of belong to every module. So here in this example, just imagine mod 1 as having that little purple tensor. Here, the purple tensor is a regular normal plane tensor. If it's filled in, it means it's frozen. And if it's slanted, that's our NF4 tensor, which is like when you've QLoRified your linear. And the reason this is what we care about is because this is what FSDP would care about. Because if you imagine wrapping every module as one layer, how FSDP would do this, it's like when it's computing layer 1, it would pause and be like, okay, I'm running mod 1, I have half of that purple tensor, give me the other half. And in this case, that little orange sliver is going to be the purple tensor from mod 1. You could go further. You could wrap more modules together as an FSDP layer. So in this case, if you wrap both mod 1 and mod 2 together as one FSDP layer, you can imagine that that little orange box becomes bigger, because it needs to pull in both the param from mod 1 and mod 2. So this FSDP is flexible. It gives you that freedom for how big you want that layer to be by giving you certain wrapping policies. But enough of giving you enough freedom about memory. You don't have that freedom, because we're OOMs, right? Like, we don't have that luxury right now. Let's get back to our main track. But don't forget things, because it will become important later. All right, so let's say you do FSDP, you still OOM. What now? Well, don't forget that you have a CPU. This is something we call offloading, which is, hey, those params, the atom state, what if we could move the parameters onto CPU and never bring them onto GPU in the first place? Or you'll bring them in small pieces. You don't want the whole chunk at a time. So what you do is you keep your parameters on CPU, and because you're doing your param update on CPU, you can move the optimizer state there too. And that's two massive chunks of your memory that's just like shunted off to CPU, freeing up your GPU to do the forward, backward compute that's like really critical, really fast. And this API exists today. You could use it with FSDP. And yeah, congrats, you don't have OOMs anymore. But what if you do that and you no longer have OOMs in this world, but it's really slow because communication is slow? And remember that for FSDP, you need to constantly bring params forward from each GPU, and then kind of move it back. So I guess this is a really crude interpretation, but like imagine you have 20 kids and you need to go pick them up from school. If you go and pick up one at a time, it's like not very efficient. But if you could go get a big van and do 10 at a time, it's way more efficient. So in a sense, if you could wrap a bigger layer in FSDP, like, you know, you can think of it as, ooh, maybe that's more efficient. So can we do more and wrap more at a time? And the answer is with FSDP1, you cannot. Why not? You could wrap mod 1 and mod 2, we did that earlier, but if you tried wrapping module 3, 4, and 5 together, note that the tensors are different shapes, they're different types, they have different required grads. FSDP1 would yell at you and be like, this is not permitted, it is not allowed. Why not? The reason is because FSDP1 uses flat parameter, which is it takes all your parameters, all your tensors in one layer, and it puts it as one tensor. And if they don't agree in type, or it requires grad, or subclass, then it's gonna complain. It's like, I can't be the same tensor as that guy over there. This is bad. This means that it's very limiting. You can't put the QLoRa NF4 tensors and your normal tensors into one wrapping. This is not great, but what if I tell you that FSDP2, which does not use flat parameter, allows you to do this? In per parameter FSDP, instead of putting everything into one flat parameter, we allow the parameters to be sharded and maintain their own identities pretty much. So you can imagine that we are able to wrap this because there's no such a restriction that everything in one layer needs to be one type of tensor, one class of tensor, one requires grad anymore. They're able to kind of coexist together in one layer because that's just how, that's the increased flexibility of FSDP2. And yeah, this is one reason, or this is one pro that has allowed us to easily compose FSDP2 with QLoRa. So it's not to say this hasn't been done before. Answer.ai actually went ahead and hacked around FSDP1, really put their heads through a lot of work and made it work. We were like, that's really impressive, but here, let's actually do something about this so that it's easier and more hack-free and shorter to write a recipe. And we did. Thanks to the FSDP2 people and Wei, there is now a torch tune recipe that you can try out that composes FSDP2, NF4, and torch compile all in one recipe. And one cool thing is we made CPU offloading faster thanks to Intel because we now have fast CPU Atom W and Atom and AdaGrad and some others. But yeah, thanks. Okay, back to our main story. What if you still OOM? Remember that both QLoRa and FSDP hammer at the parameters, and therefore they do reduce the gradients and the optimizers. But if you're full fine-tuning, like QLoRa just doesn't work for you, or if you're still OOMing after all of this, can you do more? And the answer is you can. You can do more. Remember that we were going to target more things. So first we're going to target the optimizer state. Remember the optimizer state is the blue little thing over there. And there's a lot you can actually do to the optimizer state. You can offload it. You can do the same idea where you move it to the CPU. You can turn it from 32-bit to 8-bit, maybe even 4-bit. Thanks to Gall-Nurst and TorchAO, those APIs all exist today for you to try out. And also thanks to me, I wrote Adafactor. It's not that Adafactor didn't exist before, because it did, but now it's in PyTorch core, so go try that out. And in effect, what you can imagine for the memory usage is you go from that big blue box to a much thin sliver, and if you're offloading, that blue box is essentially not even there. And note that in both those cases, your peak memory comes down a lot more, even in unrelated worlds like here, because it just sits on top of that memory. But okay, let's talk about the more, in my opinion, the thing I've worked a lot on, so in my head it's more interesting, but it's the final challenger, going after the activations. So if you asked someone on the street, don't go ask people on the street, but if you asked the person next to you at this conference, hey, I'm OOMing because my activations are too large, what do you think they'd tell you to do? They'd be like, hey, have you tried activations checkpointing? Probably. And that is today the incumbent favorite for tackling activations today. And in essence, what is that? It is, instead of saving all these tensors in the forward so that you can have them in the backward, activations checkpointing says, save less, just do more work later. Great thing for memory, bad thing for life, do not do that. Note that you're saving less tensors here, but you are paying the cost of recomputing, which is why you see little peaks in the backward. to get back those things you didn't save before. And the one thing about activation checkpointing you'll find out is you're going to apply it, you're going to see those little peaks in the backward, but you're going to realize that no matter how much you try with AC, you can only go so low. You still got to save some tensors, because if you don't save some tensors, you're going to basically recompute your forward, which means a big, big triangle here, which means you'll OOM again. So like, no matter what, you still got to save some tensors. And you'll note in every trace with activation checkpointing, there will be this triangle that you can't seem to get rid of. And today I'm here to tell you that you can. You can get rid of it. Well, how? Remember our friend, the CPU? Well, instead of saving your activations to GPU, you could offload them to the CPU. So in essence, what would that look like in your memory? Instead of having this big triangle here, it's gone. Where is it gone to? Well, it's gone to your CPU. And this is what a real profile would look like. The big note here is to realize there's no triangle. So it's kind of getting close to our brick ideal. And you might be like, okay, there's no free lunch in this world. What's the challenge now? And the challenge now is speed. You can imagine that offloading must cost something, and it does. Because you're moving things to CPU, that takes time. Those copies back and forth are costly. And the more you offload relative to your compute, the worse the perf hit. Or if you speak LLM, the fewer tokens per second. And so what if I tell you that you could actually offload in parallel? So in our previous world, the offload and the compute happen in single file. They kind of have to wait for each other. But what if I say that because offloading is independent from the compute, you can actually move that to its own line, to its own chain of events. So in CUDA, we use streams to do that. And note that in this world, it's as if your compute was never bothered in the first place. So what does that mean if this were possible for TPS? It means that you basically don't lose TPS even though you save memory. So note that the green line here is your baseline. The model I'm running is a Llama 3, sequence length 8K, batch size 4. Oh, maybe this was batch size 2. Yeah, batch size 2. Doesn't really matter. You have a baseline. If you offload with or without overlap with streams, you save about 4 gigabytes of memory, no matter what. However, if you look at the TPS hit, note that normal offload, you will lose some tokens per second. There is a gap there, you can see it. But if you use streams and you're able to do the heuristics correctly, you have the potential of getting those memory wins with no runtime hit, which is pretty cool. So yeah, if you're like, so is that possible or are you like kidding us? It's possible. We have an offloading activations offloading context manager in TorchTune that you can try today. It's actually really easy. It's just a context manager. It looks like that. Click on the link. And you might be like, okay, Jane, if it is so awesome, then why don't we offload all the time? Like, this feels like something we should just always do. Well, again, no free lunch. Offloading requires resources. If you offload a ton of things to your CPU, you could crash your CPU. You might run out of RAM. And also, the API using streams and CUDA is quite based on heuristics. This worked out for llama-based models with some tuning on my end. And it should work if you're also doing a llama-based model, but I'm acknowledging there are a bunch of other models out there. So streams is not one size fits all. And even then, even if it was one size fits all, offloading everything is not really something that you want to do all the time. Because even if you could overlap. Because sometimes the thing you're offloading is so large compared to the amount you're computing for it that it's just, you're going to introduce gaps in your profile, which will make things slower. Yeah, so with that, the recommendation or the things you can do is realize that the whole point of all these techniques is that they're composable. So in our world, in the nice results graph I showed you earlier, it used both activations checkpointing and offloading together. And it's possible to do that today because that's what this whole work stream was all about, getting these techniques in a composable manner. And if you're wondering, okay, what does the memory look like? You'll see here that basically you don't save anything in the forward, and you'll use activations checkpointing to compute some in the backward, noticing that you are still saving quite a lot of memory. So yeah, finally, the real profile from our trace is you get this nice, beautiful brick. This is the result with both checkpointing and offloading and compile. So it's very nice. And so yeah, the conclusion for you is if you are training a model and you're running out of memory, or if you just want to maximize your memory usage, get a memory profile, look for the peaks, take some of these hammers, hammer down those peaks, and let me know how it goes. And hopefully with that, you could fit more on your GPU. Yeah, everything we presented today is made possible through awesome people. Obviously, it's not just me. So like we have Les, who wrote and prototyped activations offloading, and also explored optimizers. We have Driss, who wrote NF4. He's not here today. We have Wei and Andrew, who are our FSDP2 experts, super helpful in getting it working with QLoRa. And Rohan, Evan, and Philippe, they're the Torch Tomb people. They helped review a lot of code. And of course, Albin, who just knows a lot of things. So yeah, thank you.